Hi, I'm Alvin. I study programming languages. Specifically, I like looking at programming languages from the programmer's point of view, so that's stuff like tooling, syntax, and code transformation. Here's a paper that aims to help existing code bases transition to using this new feature in the 2020 version of C++ called modules. First off, what is modular programming? It's a software design technique where you build programs with independent, interchangeable modules. Independent, as in their implementation details can be coded without interfering with others. Also, modules can't cyclically depend on each other. Interchangeable is similar to object-oriented programming principles, but it's more about the high-level build flow of the entire program rather than individual objects. Think of a module as a packaged library. As stated, pre-C++ 20 code doesn't have modules. This means that a function is either accessible to only the CPP file or accessible to all CPP files. This can lead to name clashes, also known as ODR violations. Note that modular programming can be achieved using namespaces and coding discipline, but modules enforce it. Here, the compiler compiles each CPP file separately and ends up with an object file with a set of 4 declarations it needs the linker to provide and a set of externally linked symbols to give to the linker. Then the linker connects up the loose ends. If it looks a bit messy, that's because it can be. Hence, modules to add some structure. Here's an example of an ODR violation, and here's how modules solve this problem. Now internal details don't leak into other parts of the program. Another thing is that preprocessor macros are arguably too powerful to be used so frequently. Ideally, we want features that exist within the C++ language rather than having potentially arbitrary text being added to each build. Here's an example of a module A, which uses module B. It also has a private function 4 and an exported function 6. The strategy the authors came up with is to refactor into a Unity build for each module. A Unity build is when you include CPP files. This is sometimes done in codebases to drastically decrease full build times, though at the cost of breaking encapsulation somewhat. I suspect they did this because it's simpler to prototype. Step 0, the users provide the desired clustering, such as, I want each folder to be its own module. Step 1 and 2 refine that clustering so it doesn't have cyclic dependencies. And steps 3 and 4 actually make the changes to the code base. For step 1, they leveraged the Szalay libtooling infrastructure to get a symbol dependency graph, which they aggregate into a file-to-file dependency graph. They also fix up some of the name clashes that come from using Unity builds. This part of the paper I don't like. It's somewhat unclear and they don't provide artifacts. My interpretation is that there are 2 steps, splitting and merging. Splitting ignores 4 declarations and removes cyclic dependencies by breaking modules into smaller ones. Merging then considers 4 declarations, removing cycles by combining all modules in a cycle. So at the splitting step, we keep breaking a module into smaller modules. Then at the merging step, let's say the third depends on the second, for example, then these 2 will be merged together along with whatever's here, but this one will be left alone. Here we remove the includes and replace them with module imports. We also fix the Unity build problems. And then we produce the module files in clang commands to compile them. They ran this on 2 code bases, an XML parser and a code navigation framework. They set up 3 configurations for each. The entire project as a module, which is essentially a true Unity build, each folder as a module, and each CPP file as a module. Then they analyzed how long each step took, the structure of the end result, and some analysis of the resulting code base. They discovered some bugs in the process, as refactoring always does. The refactoring process is fairly quick, and we see that Xerxes tends to collapse into one huge module, while Code Compass tends to retain its original structure. They found that the structure of codebases is closely linked to the way they are used. For example, the XML parser is shipped as a single library, while the code navigation framework is modular by design. It's also worth noting the performance characteristics. XML parsers are optimized for speed, while code navigation frameworks are optimized for flexibility. A key takeaway is that upgrading existing C++ software projects to use modules will usually require project-specific knowledge. A key thing to note is that modules add structure to the code base, which restricts development outside those bounds. So you want to make sure you get it right, or you'll end up with spaghetti code. I came into this wondering, what problem does C++ modules solve? Put simply, they represent their own library. As such, they are more heavyweight than namespaces since they affect the build process. This paper does leave a number of avenues to explore. For example, Unity builds aren't great from a programmer usability standpoint, and there are a number of alternate algorithms I can think of. In particular, I think an interactive method where a person sees the dependencies and fixes their clustering accordingly is better. I think it's quite useful to consider the reasons behind a programming language feature rather than using them blindly. Of particular surprise to me is that the more I learn about programming languages, the more I realize that the concept of what is good code is very much a research problem, and the answer is context dependent. If code prior to C++ modules was considered good, is it now considered bad? Is it okay to sacrifice code modularity if performance matters more? And what is the Pareto frontier of all of this? These are all fascinating questions, and I'd love to know what you think.